Hello, my name is Vicente Sandoval Jr. and this is my video on Mayan math. So I will be recording through here, but I will be using my iPad to then write, which you will be able to see. I'll edit it later, but just clear all this. Okay, but pretty much just to give a little bit of context, the Maya civilization is one of the many major civilizations to thrive into sophisticated and culturally advanced people in the pre-Columbian Americas. The Maya region covered what is the modern-day Yucatan Peninsula, Belize, most of Guatemala, and small parts of northern Honduras and El Salvador. As you can see here, this is the Mayan region, the yellow region, the image below. And the Maya was it's like an umbrella term for all the various settlements and villages that existed within this Maya region. And the settlements in this Maya region thrived and lived from around 2000 BC all the way to 1521 when the Spanish came and depopulated the area. Now we can move into some math. So the enumeration system of the Mayans consisted of three symbols. We had the shell, the dot, and the bar. The shell was 0, the dot was 1, and the bar was 5. These three symbols were the basis for the Mayan vigesimal or base 20 number system. So this base 20 number system was actually a vertical positional system. What this meant is that instead of our horizontal positional system where it's from left to right, from right to left, it's the ones, tens, hundreds. To them, from bottom to top, it was the ones, the 20s, the 400s, 20 to the power 3, 20 to the power 4, and so on and so on, in vertical order. So again, just the bottom place would be the ones, next would be the 20s, next would be the 20 to the power of 2, 20 to the power of 3, so on and so forth. An example that we can use for this is actually, we could just use the example of 2023. And very quickly, I also do want to paste this image right here, which is all the numerals of the Mayan number system from 1 to 19. As you can see, an example like 11, which required 2 bars, 2 fives, 10 plus 1, and so on. So we can use 2023, and if I can just expand this out to 5 200s, 520 to the power of 2 plus 120 plus 3. And so if we were to write this in their positional form, the bottom position would be 3 dots. The next position would be 1 dot for the 120s place, and for the 400s place, it's going to be 5 dots or a bar. Again, I will label these on the side. Okay. And we can also rewrite this as 5, 1, 3, very similar to the way we translated Babylonian numerals into our numerals in horizontal form, so it's easier just to translate it. Another example I do actually want to do is 69,420, which when we expand this out will be 8 times 20 to the power of 3 plus 13 times 20 to the power of 2 plus 11 times 20 plus 0, 1, which in horizontal form will just be 8, 13, 11, 0. And if we were to write this with my numerals, again, in the bottom position, we are going to have the shell, which represents 0. 11 is next, which will be 5, 10, 11. 13 is next, 5, 10, 11, 12, 13. And then 8 with 5, 6, 7, 8. Again, this is the ones place, the 20s place, 20 to the power of 2, and 20 to the power of 3. And the reason why I want to use this example specifically is to showcase the placeholder duty of the shell. And pretty much, the shell was just like a placeholder value for whenever 0 was needed, whenever there were 0 values of 1s, of 20s, or so on and so forth. And the zero was very significant to Mayan beliefs. The idea of absence, which creates space for existence, and it's just how life is a constant cycle of existence on existence, starting over and over and over again, and which is the basis of the Mayan calendars, which we will get into later. Next, I do want to get into addition and subtraction, which worked very similarly and very intuitively, where we just had our two numbers written in Mayan form and added from left to right and carried when we needed to. So an example I want to use is 266 plus 332, which translated into Arabic numerals would just be that. So we can rewrite this into Mayan numerals. So we're going to have 6 in the bottom position, 5, 10, 13 next, plus 12 here, 5, 10, 11, 12, and then 16, 5, 10, 15, 16. So we add these together, we just add from left to right. So we have 1, 2, 3 bars in the bottom, 1, 2, 3, 1, 2, 3 ones. And now we move on to the 20s place. We have 5 bars and then 4 dots. As we can see, we have 4 bars, which remember, if we recall, a bar is 5. So 4 times 5 is 20. So since we have a full 20 in this, we can actually carry 1, 2, 3, 4, these 4 bars. And these 4 bars would actually become a 1 in the 400th place, followed by everything else. So if we translate this into Arabic numerals, we get 1, 5, 9, 5, 10, 15, 18, which should equal 598. Subtraction worked the same, where instead of carrying, we obviously would borrow 4 bars from 1 dot in the position above. So if we were to subtract from this 1 dot in the 400s place would turn into 4 bars in the 20s place, and so on and so forth. So also the Mayans did have a very strong understanding of decimals. To us would be decimals, but there is no set symbol that researchers know decimals, but they have resorted to using the cuadro vigesimal, or the vigesimal square. And an example of this would be if we take 55.5, and this is going to equal 2 20s, 15 ones, and again using the Babylonian form that we once used, this will be 10. So if we were to write this in my numerals, we get 2 on top, 5, 10, 15, and there would be a little square to signify the separation of the ones in the vigesimal, and then 10. So with this, we can then move into multiplication and division, which both used an abaco, or a square grid, to which corresponds to the number of place values needed. So what I mean by this is, if we just take an example of 45 times 25, which can be rewritten as 2, 5 and 1, 5, we would use a square grid where on the left side we will have one number. So let's say we have 45 on the left side and 25 on top. So we are going to have 2 dots here and a bar in the ones place. And again, just written as how it would be regularly. And on top, we're going to have the numerals actually rotated horizontally. So the 20s will be here. 20s, let me actually just move all this. 20s, ones place, 20s, ones place. So then here we'll have the 1 dot for the 20s and the bar for the 5. So then we just use an aerial model type multiplication, which is used by high school and middle school teachers to help with the understanding of multiplication. So we can just do the 2 times 1 here, 2 times 5, 5 times 1, 5 times 5. And we can actually state, as they did, this is the 400s place, this is a 20, this is a 20s place, this is a ones place. So we can actually just move everything over here. So in the ones place, we're going to have 1, 2, 3, 4, 5 bars. In the 20s place, we're going to have 3 bars. And the 400s place, we're going to have 2 dots. Again, we can carry these 4 bars to then be 1 dot, which then equals 2 dots. 5, which translated will be 2, 5, 10, 15, 16, 5, which should equal 1,125. So division worked very similarly, where instead you would use like a Sudoku type method of, we would put the quotient inside the box, the divisor to the left, and then the dividend will be in here, the divisor will be on the left side, and then this will be empty to find the quotient. And in text I have an example where I do a little bit of trickery to figure that out. Now we can move into the Mayan calendars, where the Mayans are said to have mathematized their idea of time and religion due to their very complex calendar systems that came from their vigesimal system. So the first calendar I want to get into is the Tolzin, or the sacred round, which is a 260-day cycle comprised of a 13-day cycle that ran concurrently with a 20-day cycle where each day had some god named related to it. And the fact that it was so these two cycles ran concurrently to make the 260-day cycle, and we can actually prove that that a day only happened once in every cycle, because if we use the least common multiple of 13 and 20, we get 260. So in this cycle, no day would be repeated. And this cycle was used to like record birth dates and to follow like religious ceremonies. And this days in this cycle were written in an IDJ format, where I was a number between 1 and 13, corresponding to the first cycle, and J was some number between 1 and 20 for the 20-day cycle. And so an example of this, let's say if we wanted the 8th day in the 13th cycle, and the 4th day in the 20-day cycle, we would rewrite this as 8 D4, and there's a table I have in the notes to show what D4 would be, which it turns out to be 8 Kan, and Kan would have some hieroglyphic hieroglyph to for that specific god. Next, the next calendar we can get into is the vague year, and this vague year, or the Hab, was a 365-day cycle, which comprised of 18 god named months, if we could call them that, months, and each month was a 20-day cycle. So this comes out to 360, and so they also added 5 residual days, which to them was a very dangerous time where spirits were all over the place. So again, this worked, exactly like our 365-day calendar. And days in this month, in this cycle, we can say are formatted in an MAK format, where M is a number between 1 and 20, K is a number between 1 and 18. So an example that I have in the notes as well is, let's say we had the 5th day in the 20-day cycle, and in the 15th month, or the 15th 18 cycle, we can say this is 5A15, which is the same thing as 5 Muwan. And again, I have a table in the notes that shows what each month was named after. Next, we have the calendar round, which is actually a combination of these two calendars running concurrently together. And because these 2 days ran concurrently together, a single day would not repeat every 18,980 days. So a day in this calendar would be labeled as 8 kan, using the examples before, 5 1, with the sacred round day being first and the vague year being next. So we can prove that a day like this did not occur once at all until the 18,980 days, again, using the least common multiple of 260 and 365, which comes out to 18,980, which is days, my bad, which comes out to 73 sacred rounds or 52 vague years. And this calendar was very efficient for recording dates in everyday commerce, because a day in this calendar would occur once every 52 years, so a day would occur once about every lifetime. So what if they wanted to calculate dates or events past this 52-year round? So they want to calculate something in the past or something in the future. They would then use the long count calendar, which was a modified base 20 system that they used. So where the first unit, or the day, there was a 1 day, 20 days made 1 month, 18 months made 1 year, and 20 years made the next cycle, 20 of those cycles made the next one, and so on and so forth, working in powers of 20. So for the sake of time, I will actually just show the example from the notes, which is right here. Yeah, so which is right here. So then this example is, so the 17th day of the 4th month of the 8th year of the 3rd round of years of a 13 whole round of years of those years, which will come out to 1,176,596 days from the start of the new modern cycle, which to the Mayans was the start of the new world that they live in. So having these 4 calendar systems, actually through the use of modular arithmetic, mathematicians were able to decode and calculate within these different calendars. So if we wanted to, an example is, we wanted to add and subtract, which within the first calendar, the sacred round, we would use this method. So recall using the IDJ format such that I is in 1 to 13, J is in 1 to 20, and n equals the number of days we're adding. We can then calculate IDJ plus n will equal this statement, I plus n mod 13 d, and the next value will be j plus n mod 20. So an example, which is the example I used in the notes, let's say we had 8d14 and we wanted to add 45 days into it. So using this method, we can just go straight into it. So 8 plus 45 mod 13 d, and 14 plus 45 mod 20. And in the notes, I have the whole work going through it, and we will come out to the day in the calendar after 45 days will be 1d19. Yeah. Next, if we want to calculate within the vague year, so add and subtract within the vague year, we will use a different method, which is actually a lot more complex. So again, recall we have the MAK format such that M is in 1 to 20, K is in 1 to 18, and again, these correspond to the different cycles that we named prior, and N is the number of days added. We have N prime equals 20K minus 1 plus M plus N mod 365, and this is to find where within the 365 days it falls into. M prime is going to be N prime, what we just found before, mod 20, to know in which day of the month it falls into, and K prime is N prime minus M1 prime plus 20, all divided by 20, and this will be used to find which month it falls into, which we can then use that N plus MAK will equal just what we found, M prime, K prime. And I have an example in the notes where it goes through it, and yeah. Or I'll actually go through that example. So let's say we wanted to add 321 days to 14A5. So we're going to use above N prime. So it's the same thing as MAK. So N prime 20K 5 minus 1 plus M 14 plus 321 mod 365. We will get the N prime equals 50. Then we can move on to M prime, which is just going to be what we got here, mod 20, which equals 10. And K prime is just 50 minus 10 plus 20 divided by 20, which we get is 3. Therefore, the new date that we find is 10A3. So we moved from the 14th month to the 10th month after 321 days. Next is adding and subtracting within the long count calendar. And I do want to point out what I did do in the long count calendar in the notes is I translated it into, again, the horizontal vigesimal system. So this 1,176,000 days would also be the same as 8, 3, 8, 4, 16 days, where the 16 is in the ones place, the 4 is the 20s place, 8 is 18 times 20, 3 is 18 times 20 to the power of 2, and 8 is 18 times 20 to the power of 3. So an example we have is, I will just show it here as well. So we're going to actually use that horizontal format of writing the number to just add and subtract directly vertically. So if we have here, if we want to take away this amount of days from this amount of days, we could just subtract directly, and reminding ourselves that when we are borrowing from the place before, we will be borrowing a 20 or an 18, not a 10 like we usually do when subtracting. And and then lastly, I do want to get into finding the difference between dates in the calendar round. And just recall, the calendar round is the calendar that combines the two smaller calendars, the sacred one and the vague one, and the vague year. So because days in this calendar are recorded as 8 Con 5 Muon for the two different calendars, if we're going to take away or add dates, we're going to have to use both methods of modular arithmetic, which, because the two methods are very different, as we have just seen before, it requires a lot of steps. I did include a link in the notes to showing all the work that I went to find the number of days between two dates in the calendar. but pretty much just to give a brief overview of the steps. So firstly, you have to subtract the two dates, and you will, using the two different modular methods, where you will end up with three different modular congruent statements that all equal each other. And having this system of congruent statements, you can simplify them to similar factors, and then you go one by one using Euler's Totient theorem 3 times to find the difference between the two dates. And again, I do have a link down here which links you to an image that I have online showing that I went through all the steps. And I don't, again, right here I wrote that this calculation will take up much space and is not totally necessary to understand that this calculation was indeed possible. It's just a very laboring calculation. And that is about it. So just a brief summary of what I showed you today. The Maya were a very sophisticated Mesoamerican civilization. They used a vigesimal or base 20 system that used dots, bars, and a shell to denote 1, 5, and 0 respectively. They very much knew and had a valued concept of zero. The methods for the 4 operations exist and were all very intuitive. They had complex calendar systems that aided in their accurate calculations of astrological cycles and predictions, and modular arithmetic is crucial in decoding their calendar systems. And that is it. Thank you.